Some of you may heard me giving a similar talk, but with slides earlier in this institute. But hopefully not too many people have heard that. So you will find that what I talk about is very related to the talks of both Steve White and Brian Swingle, but kind of from a different angle. So it's also what I'm trying to the problem I'm trying to understand is very similar to what Brian is talking about. Is related to this holography. So I won't give any review of holography or this ADS-CFT duality. I guess this is working. Yeah. So but maybe I will just explain a few words as a general motivation. Actually, let me write down the reference before I write down my. My pad died, so I can't find the archive number of my paper. Anyway, I will do that later. So basically, we know from this works starting from string theory, there is this holographic duality, which at the beginning it was known as ADS-CFT. So it's a duality, so it's saying that two theories which looks very different are actually the same theory. And later we understand that it's not only restricted to conformal field theories which are mapped to some special geometries in gravity, but more generally it can be generalized to other spaces. In general, there is some gravity theory in d+1 dimension. And there is a corresponding quantum many-body system or non-gravity system, which means we have a Hilbert space and everything, as we are familiar with. And then that's in d dimensions. And then in general, this kind of duality is known to occur in some special series. And there is some reason that we, as condensed matter physicists, are interested in this because it seems that this is not something very specific for some like only very special series, but there is some general physical reason behind this duality, which is related to this renormalization group. So the general picture that was proposed was you can understand this emergent dimension as an energy scale. So as Brian already drawn earlier, you can introduce this extra dimension and then think that as if it's an energy scale of this many-body system. So think this as for example, 1+1 dimensional system. Then roughly speaking, it's like you describe the renormalization group. Then there is this renormalization group equation, and that's sort of like the equation of motion for the bulk theory. So these are just some ways to help us to understand why there is such a duality. I'm not going to use any of these as my assumptions, or I'm not going to use anything about this gravity. So now the question is, what's the best way we can understand this duality more precisely? And what I will talk about today is I'm trying to propose a very concrete procedure to do this duality, which may be different from what is already known, but at least it's something that starts from things we understand, which means this side, and then try to explicitly map to the other side. So basically, you start from this d-dimensional many-body system, and then I try to construct this mapping. This is what I call holographic mapping. And then the other side should be a quantum gravity, which I will call it quantum geometry, because I will try to understand this in some simple geometrical quantities. So this is basically the same kind of arrow as Brian drawn. Like you start from qubits, which means a many-body system, to some quantum geometry. But you will see there is some different structure coming in here. So to do this mapping, then our purpose is now I'm given a many-body state, which may be very simple, which may be a free fermion state or something that's very simple here. And then given this state, I'm trying to read out some information about the geometry that the system lives on. So this is very different from usual approach in ADS-CFT, where you already have a well-defined gravitational theory here, and you take some semi-classical limit and go this way. So here we try to read out the geometry from many-body state. So to do that, I would like to, before going to the detail, I would like to describe this approach in two basic principles. So two very simple thoughts about what the quantum geometry should look like in a many-body system. So the first principle is so basically when we think about geometry, then I don't know, mathematicians have a more advanced way to think about it, but what I will do is I will naively take the analog of Riemann geometry and ask, okay, what can we do something like that in the quantum systems? So then for Riemann geometry, the key thing is you have points in a manifold, and then you define distance between points, right? And this distance is given by the geodetic distance is given by some metric, and then you are done. Everything else is a function of the metric. So here then in the quantum system, if we want to understand its geometrical properties, then we can also ask these two questions about points and the distance between points. So then we don't know in general how do I define these things, but there are some general principles I can assume, which seems reasonable to me. So the first thing is about what do you mean by points? What's the definition of points in a quantum system? So we know in a many-body system, when we say we have this real space size, so think about discrete geometry. Then think about discrete systems, so you have lattice size. And then we know what that means is my Hilbert space has a direct product decomposition. Right? So the Hilbert space is decomposed to a product of Hilbert space on each side. Okay. However, this is this is not a unique choice. So if I just give you a many-body, say I give you a many-body system, I say I give you a fermion system which looks like this. But I didn't say what do I mean by this I. There is some label, right? So the Hamiltonian is a metric, right? So I can just do transformations, go to different bases, and then say in momentum space it may look diagonal. And then you can choose some other basis, like the wavelets Steve talked about yesterday, which will show up later in the talk. So you can choose any basis, and then in any basis you can view it as if it's real space, right? And for any of this basis choice, it gives you a set of direct product decomposition. And the different decompositions are related by unitary rotation in the Hilbert space. As long as I assume every side has the same dimension of Hilbert space, then they are just related by rotation. Unitary rotation. Right? So the first point is saying that the definition of point corresponds to a choice of direct product decomposition. And so far, the choice seems to be very arbitrary. But then, of course, we don't. I mean, we know some choices are better than others. Like if you choose momentum space and you try to describe physics in momentum space, then what you see is, say, I have a Fermi surface, and then everything is occupied here and vacant outside. But then you see physics is very non-local once you introduce the impurities. Then there is something that can be scattered arbitrarily long distance in momentum space, right? So there is no locality once you introduce the impurities. But in real space, in what we usually know as real space, this doesn't happen. You have something that's moving around, but if you have an impurity, then it's scattered, but the physics is still local. So I would say locality is what distinguishes some bases with other bases. When you consider a Hamiltonian, when you consider a system, or you consider a family of systems, then the basis where the physics is local should be the sort of correct basis where you can define geometry. But how to quantify that? That gives that's related to the second point, which is about distance between points. Second principle, distance between points. So basically, what I want to propose is that we need so for every choice of point, we need a way to define distance between points. And if the distance you define seems to be very weird, like then you conclude that the geometry is very badly defined, and there is some basis where the geometry is better defined. So in general, I don't know what's the most general principle that tells me what is the distance between points. But there is some very general principle we should believe, which is relativity, according to Einstein. That relativity means that I shouldn't have a geometry that's given by hand from outside. Right? It should be whatever the distance is, it should be determined by the physical correlations in the system. I mean, if you live in some universe where you have some field propagating around, you measure the distance. Whatever you do to measure it is some sort of correlation function in that world, right? It's right. You don't want anything added by hand from outside. So following that principle, then it's saying that distance should be a function of correlations in the system. And if you allow me to be more specific, this may be an assumption, but I would say that the distance between 2 points, x and y, which are 2 of these points, is a function of correlations between these 2 points, which means it may be correlations of some unknown function, but some operator. But if you consider all the possible operators in set x and all the possible operators in set y, they may be different operators, and you consider average value of them, and they may also have different time. Yeah.
Are you quantizing space or space-time?
Because I want to start from something we completely understand, which is a quantum system, so I already have a continuous time. Yeah. So in this sense, I'm not. In this sense, they are not treated equal. They are not treated completely equal footing. So space is something that depends on the choice of point, but I already have a time direction to start with because I have a Hilbert space and Hamiltonian and these things. So they are not treated completely equivalently. But however, that doesn't mean that time direction is completely given. So I can measure distance by correlation also in the time direction. You will see how that gives you, for example, ADS space where it's not something cross time, where time direction metric is changing in different locations. And I want to say that corresponds to the physical fact that the correlation in time direction also varies in different locations. Somewhere the correlation lasts longer in time direction, somewhere it lasts shorter. So these things happen. So the general principle is you calculate all possible correlation functions between the 2 points, and the distance should be some function of that. Okay, so these are the starting point I want to take, and this sounds maybe too abstract, but now I will show explicitly how I want to realize them. It may be not a unique way, but there is one way to describe the geometry in following these principles. So let's start from something very simple, which is free fermion in 1D. So let's take this as an example. So so you can consider something like this. So I'm drawing this as like, so this is like a fermion hopping on this chain, but I draw it in this zigzag way, but it's actually just a 1D chain. But this link and this link has different hopping, right? So now with the half filling, we know the fermion has so if this two hopping has the same strength, then you will have a band like this, trivial band. And then now, if you introduce this dimerization filling in here, you will get a band folding. So after the folding, you open the gap, and then your dispersion looks like this. Okay, so so if I write the Hamiltonian in momentum space after the folding, it's a two-band model. So the model looks like C has two components, and then something like that. So then, so M is a mass, which is given by the alternating the difference of the two bonds. So I will for now. This is just a illustration of some system which is massive. If M is
C electrons are electrons. They have a spin and power.
They have a spin which corresponds to the two components, right?
Okay.
Yeah. So they don't have a spin other than that. This is like a spin.
C is like a column of
C,
like
yeah.
a spin, so power matrix X.
Yeah, C is like that, and the polymetric C, right? But I mean, the up and down actually correspond to these two. Yeah. So okay, so for now we don't need anything specific for this model. I'm just before we go to more details of this model, I will say something generic about basically we try to propose a way to translate this into an explicit formula. Like distance is some function of correlation, but what function is that? So
I would guess it should be logarithmic, right? I mean logarithmic of the end,
correlation.
but not the correlation of the end,
It should be logarithmic of the correlation function. That's what I will say.
Yeah.
So now let's first look at finite mass. Okay, finite mass, and then we know correlation functions say something like this. Let's first talk about space. Then correlation function looks like this, right? Let me write it in this way. Yeah. So some constant times exponential decay. So
concept matrix. Concept matrix, right? C has it.
yeah. So here I contract over them. I'm just taking an example, but whatever you calculate, whatever operator you calculate, it should decay exponentially, right? So for a finite, for this massive state. So then this motivates me that if I want to define the distance as a function of the correlation function, and I want to restore the familiar geometry that we are familiar with, then we simply reverse this formula. We define the distance to be, as you said, log minus something log of the correlation function. Let me call it Cxy divided by some constant. The constant is the maximum of the correlation. So, okay. So now, if you define this for this system, you restore the familiar flat space in long distance.
This is only long distance asymptotic exposure.
This is only long distance.
Short distances will behave weirdly, so your distance will be strange short distance.
That's right.
It's not x minus y.
Yes, yeah. So I will only care about the long distance behavior. So basically, this is because in general you can't. I mean, in this theory there is only one field, so I can't really distinguish the change of correlation function coming from geometry change and the change of correlation function coming from the change of dynamics. So basically, I have to just force this correlation function to have the same formula and then apply it to every different system. And then you will get the correct geometry in long distance, and the short distance you get something non-generic. But the key thing, what I want to say here is that when your system goes to a phase transition, when the gap closes and m goes to 0, even the long distance fails. Right?
But also for sure, distance should satisfy this axiom that distance between 2 points is like smaller than
right.
And for small x minus y.
Small x minus y doesn't. Yeah, for small x minus y it doesn't satisfy. So when we talk about long distance, this is okay. But the key thing, so the key thing is that even the long distance fails when you have finite mass, when you have zero mass, and that tells you why you need this holographic duality. Why it's natural to do this holographic duality. Basically, what that means is if you live in that world, you will automatically come up with this higher dimensional description because this thing fails. Because say you live in this world and then you develop physics, and in the end you find, oh, if I use this formula, I get a nice geometry and get Riemann geometry. I mean, in this case you get flat space, but if you live on a curved Riemann manifold, you will use the same formula, you will restore the Riemann geometry, right? So everything looks okay, but if one day you have a phase transition in your world, and then some fermions become massless, and then that fermion, that particle happens to be the one you use to measure your distance. Say we live in a world where photon is massive, and then one day the photon becomes massless, but we don't know. We still use it to measure distance. Then what will we find? What we find is that the distance now will look strange because the correlation becomes power law. So the distance will look like, in long distance, will look like log function. Right? Log function of this thing, which is the Euclidean distance. So naively you will say, okay, that's just, maybe I find some gravitational wave. Maybe my metric has changed. But actually, that's not what happens. I mean, if you think more carefully, you figure out that's not just a change of metric. It's not like your space becomes curved, because even if your space becomes curved, this cannot happen. As you point out, that the distance is important. That the distance must satisfy the triangle inequality, which means if I have, say, let's think about a higher dimensional manifold for a while. In 1D, it's a little trivial. So you have this flat space, and then you have x, y, z. Generically, the distance should satisfy dxz smaller or equal to dxy plus dyz. Okay, if you use this distance, you check that, it's still true. The triangle inequality is satisfied. However, it's always this, because the log function goes like this. So if you have x plus y, you will find that dxy plus dyz is always bigger than dxz. What does that mean is if you move the y around in your space, there is no point where the y lives on the geodesic line. Because if you have a curved space, you still have a geodesic line, right? You have a geodesic line, so you can find the third point which lives on that line, so that dxy plus dyz equals to dxz. So what happened here is if you have this distance, then you cannot find the geodesic line anymore, and that tells you that your geometry sort of become quantum or strongly fluctuating. You can have all these different explanations to it, but anyway, this tells you that your geometry is not a Riemann geometry anymore. But this problem can be resolved by defining a new set of points, doing a unitary transformation to a Hilbert space, find a new set of bases. And in the new set of bases, you find that this equal sign is restored. That's the reason why, yeah.
If we define length by time it takes to send light signals, for example, which is what we actually do,
Right.
then you don't have this problem.
Then it's sort of like you already start from here.
Start from where?
You already have a world where light is massless. Yeah, then you have a different formula for this.
I'm just saying that's a different definition of length. Like the
That's
time
right.
it takes for you to shoot this fermion to you and then back to me.
Yeah.
I think it's a different definition of length than the decay of the fermion correlation function.
That's right, but I think there is a but then if I mean there's some other puzzle will happen if your light suddenly becomes massive. Right? I mean, basically, I'm trying to say that if you think about the massless point as like a phase transition point, then generically you should define it this way, and then this is a special point where you see the geometry gets different and emerge a new dimension. But if you always have the massless particle moving around, I assume there is another way which tells me that there is some formula which tells me in this case is in ordinary case it's flat, but sometimes it will become critical and then you get something different. But this is just in the massive case I can make it more concrete. Yeah.
So is there any like compelling reason that we insist on the triangle inequality, like compelling physical reason or something? What I mean is that, like, it sounds like your message is that distance is just just our like mathematical abstraction of a more profound like physical reality. So, but is there like any reason that if we make this mathematical abstraction that this triangle inequality should hold?
No, so I mean, I can certainly claim that I just define some distance function which doesn't satisfy that, or which satisfies the inequality, but there is no equal sign, and I just call it a different geometry. I mean, this is actually a distance space. It's just not a Riemann space. So it's totally okay. I don't think there is physical reason why this is always satisfied. It's just saying that if you find a way to restore this ordinary distance in a Riemann geometry sense, then we have a sort of semi-classical geometry description, geometrical description of the physics in the system. So it's trying to connect what happened in a generic system, in a critical system, to what we are more familiar with. Doesn't have to, but yeah. So basically, what happened is, okay, so now in this case, I'm saying that if you use the x and y's, that's the same x and y's that you're using in the massive case, you get this weird distance. And yeah, if you can't avoid that, then maybe you have to live with it. But the interesting thing is that we can actually avoid it by doing this mapping and go to a hyperbolic space. And then, so I will describe the mapping, but the reason why it may work is that you can put this size on the circle. So every side is actually these two together. So there are 4 states on every side. So I have 2 fermions altogether now. And then you can define a unitary mapping. Since I'm maybe I will just draw it and then I will explain the meaning. So you define a unitary mapping. So now, So what this does is it's a combination of a bunch of tensors. Each tensor is actually a unitary mapping. So you see a different version of this picture from Steve's, what Steve drawn there yesterday. So you have a mapping that takes 2 sides in, and then takes 1 side this way, and the red one should be thought as an arrow going out of the plane. So say I have 4 states on each side, fermions occupied or not, 4 states on each side. Then this is a 16 by 16 unitary, which maps the 2 sides here to 2 other sides. One is this arrow, one is the red thing going out. Okay, and then the blue thing continues. So in the end, you map all these boundary sides to the red circles, and you can count the number of red circles is the same as the number of white of the blue. Right. So what you want this mapping to do is when you measure the distance in the new sites, in the red sites, which are just a different way to do decomposition in the Hilbert space, right? Because in the end, the whole thing is is not a state. It's a unitary. I would like to call it M. It's a big unitary matrix in the Hilbert space, which map these sites into the red sites. And then when you calculate the distance in the red sites, the claim is that what I will show is they look like hyperbolic space when you have this critical distance. And that is possible because that's a possible solution to this problem, because there is a sort of a now in this new basis you define a geodesic which goes through the bulk. So basically what happens is if you have points living in the hyperbolic space, then the geodesic actually looks like this. And it turns out that the distance, let me call this distance, which is the distance in the boundary direction, as x minus y, and then the geodesic distance as dxy. Then in long distance, this dxy scales like log of x minus y. And because of that, what looks like a power law correlation, which means cxy proportional to some power law, what looks like a power law correlation in the boundary actually looks like an exponential decay in the bulk. So that's why this is possible. That's why it's possible to interpret a gapless system, correlation behavior of a gapless system, as a gapped system, as a massive system living on a different geometry, which is the hyperbolic geometry. So this is the reason why this may work. But I will need to show that it actually works. So now to show that, let me define this mapping more carefully. So now let's focus on one vertex here. So although I'm using the free fermion example, everything defined by this tensor, everything here, these are generic. They can be applied for an interacting system. So you basically take two sides, and then you do this unitary mapping, which I call the U, and it gives you two output sides. And then physically, what you want to do is you want to reorganize the degree of freedom of these two sides in this way, such that the red side represents the high energy degree of freedom in the system, in the two sides, and the blue side represents the low energy degree of freedom. So when you consider a free fermion case, this is exactly the wavelet's transformation that Steve described yesterday. So which I actually found out recently that Steve has discovered that last year, but I didn't know you have a lecture online about this. So actually this mapping gives you these wavelets when you apply it to free fermion. So in that sense, you can say this mapping is like at least formally it's a many-body generalization of wavelets. So what you want to do is you want to do something like a renormalization group, but you want to do better than renormalization group in the sense that you don't throw away anything. So the red thing is what you would throw away if you are doing real space RG. You take two sides, coarse grain, and the blue thing is what's supposed to be important, low energy degree of freedom, and the red thing is whatever you would have thrown away if you do RG. But you don't throw them away now. You do unitary, you just split them. And then you take the low energy, you do the RG again, and you get some operators there, and then you keep going. So in the end, the bulk states represent the degree of freedom on the boundary at different energy scales. So say these things in the first circle represent those with highest energy scale. Say my fermion has a bandwidth W. Then everything on the first circle is like the things which the excitations, if you create a fermion there, it's roughly speaking, it's like a fermion with the energy in this window. That's the first layer. And then second layer is like W/4 to W/2, and so on. So in the momentum space picture, it's like basically if you like all this half, all these things are in the first layer, and then you keep going. Yeah.
So you don't destroy with the red ones, right?
Right.
So, but they are kind of becoming infinitely far from everything.
No, they are filling everywhere in the bulk.
But they are not going to be entangled.
They are. That's the key thing, actually. So the key thing is that the red dots, in the end, contain everything. Right? I'm just separating them in a different way, but in the end, all the physical degree freedoms of the blue are transformed to this new basis, and they are red. So the key thing is that, I mean, if I'm doing something like a momentum shell or RG, I'm doing this really non-locally in real space, then they are really disentangled. But what happens is if you do this in the real space way, they are actually entangled, and the entanglement is important for my purpose because I want to measure the metric using their correlation. So the, I mean, and this is also related to the the relation of this approach to Mera, and this is certainly a development based on Mera. So based on the idea of Mera and also on the proposal of Brian earlier that Mera is related with SCFT. So this is like a generalization of these approaches. So the relation to Mera is that if you completely ignore the Dirac product, completely ignore the entanglement of these red dots, then you get a Mera. But although here you actually get a very, very baby version of Mera, which doesn't have disentanglers. But you can introduce disentanglers and still have these red sides going out. Right? You can introduce, say, cross coupling of these two, and then you do this. So in general you can do that. But in any case, if you make an assumption that the bulk state is completely Dirac product of each other, then all the entanglement is captured by the tensor network itself. Then the state on the boundary is a Mera state. So you can say, in this sense, I'm promoting this. I'm defining a mapping instead of state, so that if I allow the bulk state to entangle with each other, then it can capture more generic state. But basically, I think the more useful, I mean, probably the main reason it's useful is, I mean, it may be useful for this purpose is that it's easier for me to read out the geometry by calculating the correlation function in the bulk rather than just put all the entanglement in the tensor network and then try to read out the geometry from the tensor network itself. It's just a more constructive way by calculating two-point function. So, okay, so now for free fermion, so now this mapping is generic, but in general it will be very difficult to calculate correlation functions because say any operator here is some operator acting on the two sides, and any operator here is something acting on the four sides. So generically it's very difficult to calculate correlations in the bulk for a given many-body system. But so I tried the free fermion example. Okay, so in the free fermion case, we have a very simple choice of the mapping. So because it's free, I can define the mapping by their action on the fermion operators. So the mapping is defined such that, say, I have this C at the first side and the second side. I didn't write the spin up down because the mapping acts trivially on the spin. So I simply take the bounding anti-bounding states. This I called A, which leaves here, and then this I call B. Okay. So this mapping, when you iterate this, this gives you a definition of all the B's on these sides. And then you see that, okay, the B here, the B fermion here, just means the anti-bounding state of these two. It's basically an anti-symmetric wave function. So B in the first layer correspond to, so B dagger in the first layer create a wave function that looks like this. right? So this is the hard wavelet that Steve talked about yesterday. So you B created this wavelet, and then if you iterate here, then this B is A here plus A here, right? So let's call it A1, A2. It's A1 plus A2, and the A is a symmetric combination. So you see that B2 in the second layer is like it involves 4 sides, plus, plus, minus, minus. So in the end, the whole mapping gives you this wavelet basis, which depends on two labels. So it's B, which I call Jn, where J labels the horizontal direction and n is the number of layers. So depending on different n, they have different size of the wave packet, which corresponds to physics in different length scale. The key thing is that they are all the important property is that they are all orthogonal. So it's just a new basis to describe the physics. And once we define this mapping, then it's straightforward to use this proposal to check what geometry do we get in this new basis. So now let's first check this for the critical fermion. So remember. So the key thing is that now my geometry is determined by correlation functions, which is determined by the state. So the mapping only fix the choice of basis. It doesn't fix the state. So I can apply this mapping to different states, like a massive fermion, massless fermion, or finite temperature. I can apply it to different states, which will give me different geometry. So the key thing is I want to make this constructive so that you don't design the geometry by drawing the tensor network. Even if for the same mapping, you can get different geometry. So let's check the different states. And the first check is for t equals 0 and equal to 0. So it's a critical fermion at 0 temperature. So you get this correlation functions, which I can. One thing I should mention is there is actually a particularly nice correlation function, which is the mutual information. But unfortunately, it only applies to equal time correlators. But so basically, what happens is I can't just use single particle correlation. I can use this B fermions at different locations, and then calculate this, which means I sum over spin. But you may ask, in general, if I have a system which is interacting, then I may not know what operator to pick here. If I pick a wrong operator, I may miss some correlation. Maybe the two sides are very correlated, but I don't see them. So to avoid missing that, you can actually define, so this is C, and you can actually define this mutual information, which is, we know, defined as the entropy difference between the two sides separately and when you build them together. So this is a nice quantity because you know this thing bound the correlation function. So for any operator here and here, this thing gives you an upper bound of connected correlation function, which says for any operator like this, I think this thing bound the square of this times some coefficient. So basically, this makes sure that if you see this mutual information decays in some way, nothing will decay slower. I mean, everything will decay in that power or faster. So that means you can define your distance either by using this correlation function or you can use mutual information. And when you use mutual information, also the advantage is you know what is the maximum. Right? The maximum is just 2 times the maximum entropy of each set, which is log 4 in nature. There's a sign. So in practice, what I use is this thing. But when I go to a different time, the problem is when I want to know the space-time distance, then when I calculate the correlations in different time, I don't know how to define mutual information. I don't know how to define a bound of correlation like mutual information. This is an open question. So I have to kind of step back and calculate correlations of these kind of things for imaginary time, and I get something like that. And I do imaginary time because in real time everything is oscillating. I don't know how to take the log and extract the leading exponential. So in the imaginary time, I can just do the same in the same way as spatial distance. I can calculate time distance in the sense like when your 2 points are far away in time, that means they are less correlated. That means when you do imaginary time evolution, the correlation function decays very fast. That means the time duration is longer. Okay, so yeah.
So the entropy inequality basically amounts to special relativity theory, right? That nothing goes quicker than light.
Sorry.
That it's entropy inequality, the I x y equals whatever. So that it amounts to that nothing goes quicker than light.
No. This doesn't assume anything. This is generic.
No, I'm not saying it assumes. I'm saying that it's equivalent. It implies, no? Or
I mean, you can consider. I mean, I think what you said is like there for any well-defined model, there is always a fastest speed, and then nothing can propagate faster than that. That's I think that's something like a Lieber Robinson bound. But this doesn't require that.
So you are not getting like an upper bound on the speed of anything just by.
No, the speed of the that's given by the state Hamiltonian. So that's not in the definition of the distance. I can apply this to different physical systems. For each physical system, there is a bound, but it's not. I mean, that's specific for each system. Yeah. So basically, okay. So now if I apply this to the massless critical fermion, what I get is I can calculate the correlation function of different points, and then check whether they agree with the geodetic distance in the hyperbolic space, in the ADS space. Right now it's the imaginary time, so it's hyperbolic space. So now we do this for one-dimensional eddy theory. So the bulk is 2 plus 1. So the bulk is ADS3. So you calculate the distance and embed them in ADS3. And actually, the embedding is determined by scale invariance. In general, you can adjust the embedding, but you can check whether this agrees with ADS3. And for example, if I calculate, say this is one layer here, this is one horizontal layer there, then you calculate distance between 2 points. And then, as a function of this horizontal distance, this boundary direction distance, or the angle direction here, it's still a log function because the correlation decays power law. So when you take a log to get the distance, then it's a log function. But this is, as I explained earlier, this is exactly what you expect in the ADS space. So this log actually is considered as linear in the distance in the ADS space. And then when you check the radial direction, like you can take 2 sites that are going along the radial direction, and indeed, as a function of the layer index. So say I have a site j in nth layer and site j in n plus mth layer as a function of layer index. So when I'm calculating correlations between degree of freedom with different energy. And indeed, you see this correlation is exponential decay, so the distance grows linear. So it's this contract that this direction goes power law, this direction is linear. This thing is the key that tells you this bulk space is hyperbolic, which means the parameter grows exponentially as a function of radial distance.
So you have same result for the higher dimension, I mean, like a Dirac.
Yeah, actually, one nice thing about this mapping, which is the simplest, the higher wavelet, is it applies to all the Dirac fermions in higher dimensions, as long as your Hamiltonian looks like something of sine k in different directions and 1 minus cosine k in different directions. this is such Hamiltonian is always on the fixed point of this higher.
But how about this Fermi surface? Have you tried the Fermi surface?
Yeah, you can apply this to the Fermi surface.
Yeah, what can?
So that's sort of like you apply the ordinary critical Fermi on RG to the Fermi surface.
Yeah.
Then you what you see is the low energy theory is not here. The low energy physics doesn't occur here, but it occurs somewhere in the middle. Right?
Oh,
Because-
everywhere or just
No,
in
not
one
everywhere.
particular
It's somewhere in the middle.
I see.
But it's not pinned down to really sharply at some
I see.
point because you are not using momentum indices. So yeah.
So the Haar wavelets have, because of their sharp edges, they have all momenta. And so since if you were thinking about measuring it with the correlation function, it's just a single particle correlation
Yeah.
function, which
Yeah.
is diagonal in momentum.
Right,
Then
right.
the Haar wavelets will always have some sort of overlap.
Right.
And then if you did smooth the representation with more distinct anglers, then you may get fairly disjoint pieces of momenta space which have a deep level. And so it seems like you would get different distances.
Yeah,
depending
that's
on
right.
the choice of the wavelet.
That's right,
Quite
yeah.
different.
Yeah, actually there is sort of something like a non-commutativity. Like if you make this direction more non-local, this direction can be more local. Yeah, so the different choices certainly give you different geometry, and this is saying that like these concepts of distance metric, these are all not gauge invariant concepts. Right? They are in gravity theory they are coordinate dependent concepts. So I would like to think the choice of mapping as like a quantum generalization of coordinate choice. It's not only coordinate choice. It's like you choose a classical background to expand around. Like you can do your string theory in different classical backgrounds, and presumably the theory is background independent. But when you expand around different backgrounds, you get different low energy theory, and they look different. But actually, when you look at spectrum or anything that's gauge invariant, that's actually the same theory. It's only theory. So I think I have 10 minutes.
Yeah.
So I hope to get to the point before getting too late. I hope to get to the point that about the black hole, because one thing I like very much is not this thing that it recovered the ADS space correctly, because that's sort of by design. Like I do an RG, and by design my Hamiltonian is on a fixed point, so scale invariance basically pin down all the structure here. So you check that it's scale invariant. So in large scale it must be ADS. But the non-trivial thing is now I can apply it to different initial states and then get different geometry. So this is like a lattice version of a CFT, and then you can apply it to non-CFT. You can so the most interesting thing will be applying to finite temperature. So for zero mass but finite temperature, then we know the correlation will look different. So if you use the same formula, you get a different geometry in the ball. So let's study what happens separately for spatial and time correlation function. So spatial. Let's look at equal time correlators, which tells me the spatial metric. So we know what happens is in the finite temperature, if you calculate the correlation function between these two wavelengths like this and this, in long distance they will decay exponentially. Right? So that means when you take a log and translate this into distance, then it's not that log function anymore, but it becomes a linear function because it basically looks like a massive state. So at short distance it's like a power law, but at a long distance it crosses over to linear. So that's what happens when you calculate distance between the two. Okay, so now what happens if you calculate this for different layers going into the IR? And what you see is that this exponential decay is faster and faster because for the same temperature, the energy scale of these things are going down exponentially. So compared to the energy scale of these particles, which means like they're hopping and things, the metric element of the Hamiltonian in that region, your temperature is higher and higher. So what you see is that, say this is like the two points both in the first layer, and then second layer and so on. What you see is this, that the slope becomes higher and higher. And actually when you go to infrared, this slope increases exponentially. So because it increases so quick, so I cannot really, at the beginning I can't really get that limit very well numerically, but later, so So now with my student Tsinghua, he has some calculation which shows analytically what's the behavior in that limit. And which basically you calculate like two very smooth wavelets and what's their correlation. And what you see is basically something very interesting. It's like, let's calculate two neighbor sites. So D, J, N with J plus 1. So it's like two sites that are next to each other that are like this. And they're next to each other. And then for different layers. And at zero temperature, they all have the same distance. Like in zero temperature, because scale inverse, this two has the same distance as these two. So now, if you ask, now I can ask, what is the area of each circle? In higher dimension, it should be called area. Here it's perimeter. So you can have something like this, and then you measure this distance and multiply it by the number of sides. So you have an area. Area of the nth layer. So at the zero temperature, what happens is when you increase n, which means you go to IR, this thing decays exponentially because the number of sides decay exponentially, and then the distance between neighbor sides is the same. But at zero temperature, what you see is that because the two sides, when you go to IR, the two sides are so littly correlated that when you translate it into distance, they are very far away. So that means, the distance between two neighbor sides actually increases exponentially, which cancels the exponential decrease of the number of sides. So what you see is this curve that saturates to a constant. What does that mean? That means that if you use this distance to use the correlation to measure distance, and you leave that world, you walk around this circle, you see this circle actually doesn't shrink to a point. You see your geometry actually looks like this, rather than the disk. At zero temperature, this is a point. And when you have the final temperature, basically your space has been burned with a hole. That's basically what happened. So that's a good sign that tells me that there is a black hole in the center. I mean, that's consistent with there is a black hole in the center. But it hasn't told me that the hole is black, because it just tells me spatially there is a hole. But what's the difference between black hole and, say, your space terminates in IR, which happens in some cases? Say, if you give the system a mass, that's one case I studied. I won't show it here. If you have a finite mass, then your space actually terminates, but your time doesn't terminate. Your time is doing normal things. So there is just a spatial boundary, a wall. But what distinguishes black hole from that is you calculate time duration correlation. So you have this disk, and then you can calculate, say, time duration correlation for two time and the same location. Imaginary time. So now it's finite temperature, so everything is periodic in time. Okay, so what you see is this thing, when you translate it into distance, which is a log of this, then as a function of tau, it's going like this, and it's periodic in beta, going like that. So, okay, so now when I move this point gradually inside, what you see is that this thing decays slower and slower, which is not surprising because the energy scale is going down. So everything moves very slowly. I mean, by the way, if you do the calculation in zero temperature, this also becomes slower. But the difference is in zero temperature, this becomes slower in power law sense. But here this becomes very, very, very slow in the finite regime here, which is defined by the regime where the energy scale is much smaller than temperature. So there is a regime where, say, your energy scale is going down like suppressed by exponential factor, and that if that is much smaller than temperature, then you basically are in the infinite temperature limit.
What's n?
N is the number of layers going in next. N equals 1, 2, 3. So 1, 2, 3 going up.
So which geometry you obtain for infinite transition?
So basically, when you calculate this correlation function in the high temperature limit, you lost the time dependence because you're already in temperature. Nothing time evolves.
But also space correlations also change, so you should get
Yeah,
something.
space correlation is what happened here. Yeah, the space correlation tells you that space correlation becomes very, very short range. So different sites do not talk to each other at all. But if you look at their time evolution, they're very slow. So that's the key which tells you there is a black hole. Because the time direction distance, this is actually the correlation function. Correlation function doesn't decay, which means when you translate it into distance, the distance doesn't grow. So in the ultraviolet, what happens is the distance grows and then decays back. So this is basically like time direction is a circle. So the distance between these 2 points grow and come back. And what happens in the infrared is this almost do not grow. So the circle, the radius of the time direction circle shrinks to a point when you approach the IR. And that's exactly what happens when you have a black hole. Like if you do this rotation of the black hole time to imaginary time, then the horizon is a point where the time direction circle shrinks to a point. Basically, when you do a rotation of black hole geometry to imaginary time, to the Euclidean time, you get a cigar shape. And the circle shrinks here at the horizon. Yeah.
So this calculation you are doing with the fermionic setting. So if you are doing it in the other setting, then would you get the same thing?
You mean in a different system?
In a different setting, like with different Hamiltonian.
Yeah, so
this is a fundamental thing. It should not depend on whether it's fermionic.
That's right. Yeah. So I don't have a proof that's always the case, but you see from this calculation that there is some reason to believe this is generic because as long as this is assuming that you have the right mapping, which does the RD job, which means any operator here is very low frequency, and the frequency goes down when you go to the infrared. As long as that's true, then when you have a finite temperature, it's always like this part looks very hot and this part looks cold, because the energy scale is different. The temperature for the boundary system temperature is the same, but because of the separation of energy scale, the center part looks very hot. And because it's very hot, then the correlation function becomes very, very short range, and that's the reason why there is a hole opens up at the center. And then there is this very slow time evolution, which gives you this time infrared shift. So this is basically, the red shift. So this is telling you that when you approach the black hole horizon, there is this infinite redshift. So I won't have time to go to any other example, but you can do this. You can read out the geometry for different input states for whatever state you like, and you can add a mass to the system, which you see there is a space turbulation, or you can introduce two chains which are entangled. Translate this into two disks in the bulk which are entangled, and you see that they are entangled very much in the center. So in the end, the two spaces are connected and become the wormhole. So you can see all these kind of things. And so in general, just one sentence about the general picture behind this is, as I said earlier, the choice of mapping is sort of like you choose a classical background to expand around. So there is, of course, ambiguity of what you choose. So for the scale invariant case, there is a sort of given choice. Then you calculate the geometry, and then you get something with the same symmetry as this thing. It has a scale invariance. But in general, there is no a priori choice. You can make different choices, and I would say this approach is sort of like you start from this classical background geometry, and then now instead of just looking at the tensor network which gives you the geometry, now you can calculate this, and this is like giving you the quantum corrections to that geometry. So it may not converge yet, but it gives you to the leading order. It tells you which direction it's going. Like this mapping may look like an ADS space, but when you have a finite temperature, it tells you it's actually an ADS with a black hole rather than ADS itself. So it tells you the direction where the geometry is going. Okay, I think I will stop there. Thank you. Yeah.
You pick specific quantum Hamiltonian, you get specific metrics. But in the AES, if your black hole is like specific metrics, but in quantum gravity, metrics should fluctuate. You should like integrate with respect to all metrics.
Yes.
All matrices.
Right. Yeah, that's a very good question. Yeah, so as I said, this is like expanding it around the
Like very classical. That's
yeah.
fixed spectrum.
So I'm not. So yeah. So one thing I should clarify is that having a way to calculate this metric and then compare it with a classical metric like AES doesn't mean this theory, this bulk theory I obtained this way, is a semi-classical gravity. Because the semi-classical gravity will have gravitons and all these things, right? I mean, it's not only about the metric, but about fluctuation away from the metric. Here, what I have is like, in this choice of, you can think of this as my geometry is still strongly fluctuating. But for each geometry, this choice of mapping gives me a way to define a coordinate on it. So I define coordinates of the points on the geometry for each of the fluctuating metrics. And then I'm doing an average over different metric, which gives me on average what the geometry looks like. But the fact that the bulk has no graviton, because the boundary is a free fermion, and when I do this free fermion mapping, the bulk is also free fermion. So the bulk only has free fermion. So you can say that's a signature that tells you it's a strongly fluctuating geometry.
So with this philosophy, can you quantize Einstein gravity?
Yeah, that's what
Einstein gravity quantum version of it with your philosophy.
I mean, that will require to find the correct boundary theory. Maybe we know it, maybe it's theory on mirrors, but it requires to do this for a specific theory, which will give me this Einstein in the bulk. And that's apparently that's the most interesting question, which I still don't know how to do.
So just the reference to your paper is 13, because you asked
Oh, yeah, thank you.
1309 dot 6282.
1309 6.
6282. This is your paper.
Yeah. Thanks very much. Yeah. Every time I forgot to give the reference. So yeah. Thank you very much. Yeah.
So in this decomposition, you took the symmetric and antisymmetric combinations. So presumably any critical theory with the k to the 0 critical modes being at k to the 0, this would work?
Well, but we basically have no much choice. Oh, you mean like I can have different z, different power, the dispersion?
Let's say you're more, trying to take critical forms, not free fermions.
Then I'm not sure, because I don't know what the k to the 0 means. I mean,
Let's say
this,
transverse field Ising model or something like that. It's a sort of free fermion.
right. So for example, for transverse field Ising model, if I first fermionize and then do this for the fermion, I will get this is like the right RD. But if I naively just take the spins and then do this symmetric and antisymmetric combination, I'm not sure if that gives me the right theory. Yeah, so for interacting theory, I don't know how to define this k to 0 or
So you
because
don't know
different
the
momentum
changes that you make to get these fields.
Yeah, correct. Yeah.
In practice, you can think about doing a Mera calculation to optimize the things that you want to keep.
Right. So maybe we find the optimized Mera, and then we ask what is the residual entanglement between the sites in the problem. Yeah. Yeah. But again, we face the problem that a correlation function in the bulk will involve many sites on the boundary. I don't know how to calculate it here. So what I didn't get time to say is, then it seems not useful for interacting system. But I think it may be useful as a variational answer. I can put some entangled but very simple state in the bulk, which is like free fermion, and then map this back to the boundary. If I put a Dirac product state, this gives you Mera. But if I use some free fermion state or something, then it gives me some different state. So maybe it gives you some different answers to describe many-body system. So I can only think that in this variational way it may be useful. Otherwise, I can't go this direction. I have an interacting boundary system and calculate the things in the bulk. That's it.
Maybe let's break and thank Xiao-Liang.
Tem visto bem, como vocês mixam lá.